We are working on the classical definition of probability, and we have seen that the classical definition of probability is probability of any event E is equal to number of outcome in the event E divided by total number of outcomes, or the total number in the sample space. Now, let's answer this question based on the classical definition of probability. Here is the problem. When a single die is rolled, so when you roll a die, you know the sample space already. You'll get either 1 or 2 or 3 or 4 or 5 or 6. So that is your sample space. And if you want to look at the number of elements in the sample space, you can see there are 6 of them. 1, 2, 3, 4, 5, 6. Now we are going to answer each of these questions. So we have to find the probability, of getting even numbers. So how many even numbers are there? What are the even numbers when you roll a die? What are the even numbers here? 2, 4, 6, right? You can unmute yourself. Okay, 2, 4, 6. That is my event. So the probability will be probability that you'll get even numbers is equal to number of even numbers divided by total number in the sample space. So the even numbers, you have 3 of them out of 6, right? Out of 6 here. 3 out of 6, which is half, or 0.5. That is the probability of getting even numbers when you roll a single die. Next is, what is the probability of getting odd numbers? So what are the odd numbers there? Tell me.
1, 3, and 5.
1, 3, and 5. Very good. 1, 3, 5. These are odd numbers. So when you find the probability of odd numbers, it will be number of the odd numbers divided by total number in the sample space. So the number in the odd numbers, you have 3 out of 6, which is also half, or 0.5. So you can see that these probabilities are between 0 and 1. What is the probability of getting an 8? Okay, so probability of getting 8 is equal to, how many 8 are here? 0, 8. There are no 8 out of 6. So what is the probability?
0.
0. So, and you already know the meaning of 0 probability. That is, this is impossible event, right? This is impossible event. Meaning of that is, by rolling a die, you'll never get an 8. That's impossible. That is the meaning. So probability is 0. Okay. Next one, the probability of getting a number less than 7. So here we are calculating the probability of getting a number. I'm writing number like that, less than 7. How many numbers are less than 7?
6 of them.
6 out of 6, right? 6 out of 6, which is equal to 1. That means when you roll a die, you'll always get a number which is less than 7. Always you'll get a number less than 7. That's why the probability is 1. Meaning of that is, this is certain event. This is certain event. That is, it is going to happen 100% of the time. So every single time you roll a die, you'll always get these numbers, which is always less than 7. But you'll not get 8. So that's impossible. And other two, you have seen 50-50% chance. So the probability is a number between 0 and 1. And the classical definition of probability is probability of event E is the number of outcomes divided by total number in the sample space, or total number of outcomes. Any question in this example? You can speak. Okay. We'll go to next one then. Here we are talking about the complementary event. We are still working on the classical probability. Don't forget that definition. The definition of classical probability. What was that? Classical probability. It was probability of any event E equal to number of outcomes in the event divided by total number of outcomes, right? That was the definition. We're still working on that, but in this, we are going to look at a special type of event or special events called complementary events. The complement of event E is the set of outcome in the sample space that are not included in the outcome of the event. Let's understand the meaning of this first. For example, you are rolling a die. When you roll a single die, what are the outcomes? The possible outcomes are 1, 2, 3, 4, 5, 6. Those are the possible outcomes. That is my sample space. This is sample space. Now let's take an event E. Suppose event E is odd numbers. Odd numbers are 1, 2, no, 1, 3, 5. 1, 3, 5. Odd numbers. Suppose that is my event. Now, when I say complement of that event, let's write the complement of the event. The complement of the event, we write this as E prime like that. Okay, it is denoted by E prime or E bar or E with this C on the top. You can use any symbol, that's okay. So I'm using E prime. That is the complement of the event. And the definition is the complement of event E is the set of outcomes in the sample space. These are the outcomes which are here in the sample space, but not here in the event. So what numbers are there in the sample space, but not in E? Look at this and tell me. What numbers are there in S, but not in E?
2, 4, and 6.
2, 4, and 6. Very good. So 2, 4, and 6. Okay. So this is the complementary event. This is the complementary event. Now, let's do one thing. What is the probability of E in this case? If you want to find the probability of E, there are 3 elements here out of 6. So 3 over 6 equal to how much? Half, right? And if you want to find the probability of complement, what is the probability of complement? Probability of the complement is equal to, in the complement also we have 3 out of 6, which is also half. Now check here, if we add these two values, the probability of event and probability of the complement of the event, probability of event and probability of complement of the event, both are half. If you add, it is equal to 1. Okay, so remember that the probability of the event, okay, probability of the event and the complement of the event, when you add those two, it is equal to 1. Very important formula. Probability of the event plus probability of complement of the event is 1. Or sometimes we say probability of happening an event plus probability of not happening an event is equal to 1. Now, if you want to just find this probability of the event, what we do is we move this probability of the complement to the other side. So it becomes 1 minus probability of the complement. Or if you just want to find the probability of the complement, then we move this to the other side. So that will be subtracted, 1 minus probability of the event. But the key here is probability of the event plus probability of the complement of the event is 1. Using Venn diagram, this is how we represent. You can see in the first one, here inside this circle, there is a probability of the event, okay? And outside is probability of not happening an event. If you add those two, that will be 1. Similarly, if this is probability of event and that is not E or complement, the total is always 1. Any question on this one before we go to the example where we use this? Waiting for yes or no?
No.
Oh,
No.
great. Let's take an example on classical probability where we use the concept of complementary events. Here is that example. Let's see what is given here. It was found that 25% of the people were victims of a violent crime were ages 25 to 30. So 25% of the people, they were the victim of violent crime and the age is 25 to 30. So when we write the probability, this is, when we say 25% of the people, the probability is 0.25, because you know that when you write the probability, it is the number between 0 and 1. So probability that their age group is 25 to 30 is 0.25. If you are not asking me a question, please keep yourself muted. Okay, so that is given to you. People in this age, 25 to 30, who are the victim of violent crime, their probability is 0.25. Okay, so if you think of the age of people, this is how we can think of. You can think somebody is starting at age 0, and then let's go up to 25, then 30, and more than that. So what we have here is, if you look at that little diagram that I've drawn, they have given the probability for this one. Probability that these people are the victim of the violent crime is 0.25. Okay. The age of the people over here will be less than 25 years or younger than 25 years. And age of people in this region will be more than 25 years, more than 30 years, or older than 30 years. Now the question is, if a person is selected at random, find the probability that the person is younger than 25, that is on this region, younger than 25, and older than 30. That means we are just excluding this. We are just excluding this 0.25. So if we are excluding the 0.25, we are looking at the complement of 0.25. Okay, so in the first one, your age is between 25 to 30. So if I want to write that little bit mathematically, I can write like this. Same thing, I'm just copying this one. Probability that someone is between 25 and 30 years. This is how I can write using inequality. If the age is X, okay, if the age is X, then the probability that age is between 25 and 30 is 0.25. Now we are looking for the probability that their age is younger than 25 and older than 30, that is the complement. So if you want to write the complement, this is how we write. Probability their age is less than 25, right? Less than 25, this one, or more than 30, or their age is more than 30. But what we know is if we add these two, the total probability is 1. Out of 1, I already have 0.25 there. So the remaining probability will be 1 minus 0.25 because the total is 1. So 1 minus this probability will give the probability on this side, these two. So we can write this as probability that X is less than 25, that is their age is less than 25 or more than 30 years, is equal to 1 minus 0.25. How much is that? You can subtract it. It should be 0.75, right? So that is the probability. So 0.75 is the probability that someone who is younger than 25 or older than 30 years is the victim of violent crime. Any question on this example? I'm waiting for a yes or no, or a question.
No, sir.
Okay, great.
Nope.
Beautiful. Okay. Now, look like we are done with the classical definition of probability. Now we are going to go to the second definition of probability, which is called the empirical or statistical probability. So let's look at this definition and what it is telling us. The difference between the classical and empirical probability is that the classical probability assumes that the certain outcomes are equally likely. We already say that. For example, if I'm tossing a coin 10 times, I think that there are 5 heads and 5 tails. That was the concept in empirical probability. I mean, the classical probability. But that is not going to happen in real life. In real life, what we do is, like in the animation we did, we perform the experiment and we record. Maybe out of 10, you'll have 9 head and 1 tail, or maybe all tail, or maybe all head, or something, some sort of combination. So we'll actually look at the data. We'll look at that frequency table. If you remember in that animation, there was a frequency table. So we'll look at the frequency table, and to calculate the probability of any event will be equal to frequency of that event, how many times that event will occur, divided by the total number of time the experiment is performed. So we use the actual data to calculate the probability. Because we are using the actual data to calculate the probability, it is also called the statistical probability, because in statistics, we use the real data. But there is one thing, here is one little graph here you can see. You can also look at this in your note catcher. You can see this is the graph showing the number of times you toss a coin and how many or what percentage of the time you are getting a head that is recorded. So for example, you can see over here, you perform one set of experiment, maybe so many times, 100 times, and you get like 75% of the time you got head. Second time you perform the experiment, you get like 65% of the time. And this is changing. If you perform the experiment for large number of time, very large, 1 billion time or so, then in that case, if you're tossing the coin, recording, tossing the coin and recording, if you perform that for billions of time, then you may see that the number of head and tail will be equal. So meaning of that is, if you perform the experiment for a large number of time, then the result that you obtain by recording this data will be approximately equal to what this classical probability was saying, 50%, 50%. So what do we say? When the number of trials are infinite, the empirical probability approaches the classical probability. If this n in the denominator, okay, is a large number, in that case, the result that you obtain in statistical probability will be same as classical probability. And that law is called the law of large number. So this is the fundamental idea of the empirical or statistical probability. We are going to take an example and use this formula to solve it. Here is that example. Let's read through and then solve this problem. Let's see what is given. A company is conducting a phone survey of randomly selected individuals to determine the age of social networking site users. So far, 1,000 social networking site users have been surveyed, and the data is here. The frequency distribution shows the result. That is, out of these 1,000 people they call and ask whether they use the social networking site, in the age group of 15 to 25, they have 175 responded who said yes. 26 through 45, 410 responded they use the social networking site. 46 to 65, 325 of them say they use the social networking site. And 65 and above, 95 of them, they use the social networking site. So here is that result. Now we have to use this information to answer this question. The question is, what is the probability that the user is 26 to 45 years old? That is the first part. We have to find the probability that the user is 26 through 45 years old, right? 26 through 45 years old. How many are there? 26 through 45 years old. Look at that. You can unmute yourself, please.
410.
Okay, so probability that their age is 26 to 45 years. In this, the frequency is 410. Frequency is 410 out of, what is the total? We already know that. That is, look at that, 1,000, right? That is the ratio. You can change this to reduced fraction. When you change this to reduced fraction, you can cancel the 0 at the end. So it will be 41 over 10. No, there's 1,000 in the denominator because total is 1,000. So it will be 41 over 100. That is the reduced fraction. You can leave it like this or change it to decimal, and the value will be 0.41. That is the probability. Probability that their age will be from 26 to 45 is 0.41. So if the frequency is given to you, if the frequency table is given to you, you have to use the statistical definition of probability. Next one, look at the second part. Second part says, what is the probability that the user is below 65 years? So probability their age is less than 65. That is the meaning of that, below 65. Do you have information about below 65? What is here? That is above 65, right? Yes, no?
Yep.
Yes.
Okay. So they have given the information for above 65, but here they have asked below 65. But what we know is the age above 65 and age below 65 are complementary. So what we can do is, you are looking for the complementary event. So the probability will be 1 minus the probability their age is greater than 65. So I use that complementary concept. So that is equal to 1 minus this one, then minus probability their age is greater than 65. How many users are there? You can see 95, right? 95 out of 1000. Now you can subtract that. That is 1 minus, you can also do this in your calculator, 1 minus 95 over 100. What you know is that will be equal to 905 over 1000. Do that in your calculator. 905 over 1000, or if you write that as a reduced fraction, it should be 181 over 200 when you write that as a reduced fraction. But if you want to find as a decimal, maybe you already got the answer as a decimal. So the decimal value will be 0.905. You can directly type this in calculator, 1 minus 95 over 1000, and you'll get this value. Okay, you can do the way you want. You can directly type this 1 minus 95 over 1000, and you'll get that value, which is quick and easy. Any question here?
No.
Okay.